Yeah, alright. So we have a wave. For this class, it doesn't matter, but this is technically a transverse wave. You don't need to know that for this class. There's two types of waves, but this is a transverse wave. What do we call this?
Crest.
And what do we call this?
Draw.
And what's a wavelength?
Distance between two identical points.
So we see it comes. So it's so if we were to start from the left and draw it, you see it's moving upward here. And if we were to continue going, it's moving downward here, so this isn't identical. And it's coming back up. This, if we were to draw an imaginary midline through that point. We see that at this point and at this point would be a wavelength. We could also have measured it from one crest to another crest. It's also a wavelength. And if I choose some random point right here, and if I were to draw a artificial line, so it's going up right here. So this point right here on the wave isn't the wavelength because it's going down. It's not identical. But if we were to continue, we see at this point where it crosses, it's going in the same direction. So from here to here would also be a wavelength. So any two identical points is a wavelength. And let me redraw this as it's getting messy. So if I were to put an imaginary middle line, called the midline, then the distance from this midline up to a crest is the amplitude. And equivalently from the midline down to a trough is also amplitude. So again, to a crest or down to a trough. And the distance between two troughs is also a wavelength. What's the equation for wave speed?
Wave speed.
Yes. Velocity is equal to what?
Oh, the speed of light is 3 times 10 to the 8.
Velocity of a wave is equal to its frequency times its wavelength. So velocity slash speed of a wave is equal to the frequency of a wave and the length of a wave, which we usually write as wavelength, which is the length of a wave. Technically, by the way, this section right here is one wave. So this is exactly one wave, the length of a wavelength. So here we have one wave, another wave, and then a quarter of a wave. So this entire length of this would be, this is composed of 2.25 waves. 2.25 waves. We could also call this a wave train. Usually we think of this whole thing as just being the wave. And when we say the length of the wave, we're referring to one portion of it. Note that this equation applies to all transverse waves, all waves that look like this. So, for example, if you are standing at the beach, we have a pier at the edge of a beach. If the distance between these two poles, let's say it's 2 meters, and you see so basically if you see that the width of the wavelength is 2 meters, if you can use the distance between the pairs, and let's say that you watch a crest go from this to here in 1 second. So you're watching this one crest. So you're watching this one crest here, and about 1 second later you see it move to right here. What would its velocity be? What is speed? Do y'all remember that from junior high? Speed is distance over time. So if you see this point right here go a distance of 2 meters in 1 second, its speed or velocity is 2 meters per second. Let me think of another example. So, a more useful example. Let's suppose that, again, same scenario. Let's say that you instead were watching this, and you see that this thing is going up and down about once every second. So you see the wave go up, down, down. So it's oscillating down and then back up at a rate of one oscillation or one times every second. That means the frequency is 1 hertz. How many times something happens every second? you could use this to actually figure out the velocity of this wave. So if you didn't know, if you knew the wavelength, if you were able to measure a distance from crest to crest, and if you knew how often this is changing, how many waves are passing every second. So let's say you see one crest pass by this pier one time every second. You can actually figure out how fast the water is moving. Or I should say how fast the wave is moving. By multiplying the frequency times the wavelength. So 1 hertz times 2 meters would give you the 2 meters per second. A hertz is really a per second. It's not really related to this class, but by the way, if we have waves in the ocean, let's say, and we have, let's say, something floating, would the thing floating move left or right? Is the water actually flowing to the right? What is a wave actually carrying with it? Y'all know? This is more physics than chemistry. If you were to zoom in and look at only one molecule, the molecules are only bouncing up and down. Waves carry energy. That's the only thing waves do. They don't carry matter with them. When we say that a wave is moving in a certain direction, note that the water isn't actually going left and right. In real life scenarios, there's gravity and it might try to go down a slope of the wave, and we might see some movement. And we might the reason why there could be a wave is because something pushes the water outward, such as you drop something in a lake, or wind is blowing, and we can get motion like that. In an ideal scenario, objects don't actually move left or right. For example, when you're fishing, if you're in a perfectly still lake, or I should say, if you're in a lake that doesn't have a current flowing, so Sam Raymond is connected to a river, right? So there is technically flow of water underneath, but usually it's still enough to where even if there's a lot of waves, do y'all notice y'all's bobber doesn't actually move that much? The only reason it's moving is either wind's pushing it or it's the current of the water. So even if a boat were to go by, the boat really shouldn't push the bobber anywhere. It should just go vertically, staying put, and it'll return back to where it is. The only thing that waves carry is energy. And they carry energy from one location to another, but again, that doesn't matter. For this class, the only waves we're looking at is EM waves. The velocity of an EM wave is the speed of light. 3 times 10 to the 8 meters per second, roughly. And we can reduce this equation to speed of EM wave is equal to its frequency times wavelength. So, starting from low frequency to high frequency. Actually, let me write high frequency on the right. What is the lowest frequency EM wave? Radio. And then what comes next? By the way, you should have this memorized. After microwave is... Then we have visible. Visible can be broken up into red, orange, yellow, green, blue, indigo, violet. Next to violet is ultraviolet, then X-ray, then gamma. This also corresponds to long wavelength and low energy. So 3 L's for one side. And on this side, we have shorter wavelength. And we have high energy. The test is going to have lots of questions. They're going to ask which has higher energy. Microwaves are ultraviolet light. You will not be given this. You'll have to memorize it. So which have higher energy, microwave or UV light? Ultraviolet, because it's closer to this side. Anything to the right is going to have higher energy, shorter wavelength, and higher frequency.
I'm already confused with which the UV and infrared.
So if you remember with radio, and you remember Roy G. Biv, and you remember that it's in this correct order, if you start with radio, then visible is going to be Roy G. Biv. Infrared is going to be next to red. Ultraviolet is going to be next to violet. As long as you remember it starting with radio, then comes microwave. Hence the reason why I always write it in this order, so that Roy G. Biv makes sense, because I believe all of y'all have heard of Roy G. Biv. So, which has shorter wavelength? Green or yellow? Yes. Green. And it's closer to the right. What EM waves are longer or have longer wavelengths than infrared? This would be radio and microwave. Do y'all remember the equation for energy?
HF.
Energy is equal to HF. I don't have y'all memorize Planck's constant. It is on the test. Planck's constant is 6.63 times 10 to the negative 34 joule seconds. Yeah, you don't have to memorize it. The speed of light, though, this value is very useful. You should never have to Google it. You should always have it memorized. In any science class, that's usually a given that you have that number memorized, because it is one of the fundamental constants of the universe. Even though it is rounded, it's close enough. which is not a visible EM wave? Orange, blue, infrared, indigo, sky blue, purple, and that's it. So which is not a visible EM wave? So infrared is not in the visible spectrum. Is that it?
Which one's that blue one?
Sky blue technically is.
What's that little
Indigo is.
sign?
Blue is. So sky blue is a lighter color of blue. I should this isn't on the test. But purple was the other one. This isn't. Purple is actually a combination of red and blue. It's not a single wave. It's not considered a true color. Sky blue kind of is, but I'll remove it just to illustrate. Purple is not a true color. It's a figment of our brains interpreting the signal from our eyes. What's the units of energy? So joules is energy. So let me illustrate that example again with the pair. So if you're sitting here watching a pair, so you're over here watching it, and all of a sudden, so it'll come over here and do. So it's moved over, so this crest is moved to here. Just putting the same mark. So this indicates the same point of the wave. And you're noticing the time it takes for a crest to reappear over this pair. Let's say that the time is 5 seconds. And you're able to measure the distance between two crests. So the distance between two crests is 10 meters. How fast is this point moving?
Meters a second.
Anyone else get something different? Yeah, I get how to solve it. So the time it takes for this crest to reappear So we're seeing basically one crest every 5 seconds. We can factor this out. So that is 1/5 of a crest per second. Right? So one crest per 5 seconds. So that means the frequency is 1/5 hertz, which is 0.2 hertz. The wavelength is 10 meters. The velocity would thus be frequency times wavelength. So 0.2 hertz times 10 meters, which gives us 2 meters per second. So, is that how you did it?
I just divided 10 by 5.
Not very rigorous. I haven't done enough examples with this, and I'm trying to do more. So, frequency, let me get this. Frequency is a measure of how many waves pass by every second. And if we simplify a wave to just look like this, to where each wave has a one crest and one trough, it's very easy to count how many waves pass by. You simply count how many crests are passing by a point every second. That tells you how many waves per second. If I changed this and said that you saw 2 waves, or I should say 2 crests, or let's do this. Let's say that you want to be very accurate. Let's say you're watching a pier, and over the course of a minute, you count 20 waves. So over the course of a minute, you count 20 crests passing a point or marker. So we have 20 crests per 60 seconds. That means the frequency is going to be 20 divided by 60 hertz, or 0.3 carried hertz. And wavelength can be done by measuring the distance between 2 crests. And let's say we do something else. Let's say that we have a pier that we know the distance between the two wooden pillars is 10 meters. And you time that it takes 2 seconds for a crest to move from here to here. So velocity or speed is distance over time. So 10 meters divided by 2 seconds gives us a velocity or speed of 5 meters per second. If I then ask you what is the wavelength of this water wave, velocity equals frequency times wavelength. Solving for wavelength, we get V over F. So 5 meters per second divided by 1/3 of a hertz. Dividing by a fraction is the same thing as multiplying by the reciprocal. So that's the same thing as multiplying by the reciprocal, 3/1 hertz. And we get a wavelength of 15 meters. That makes sense? If I say something is bobbing up and down twice a second, what is the frequency when something is twice a second?
0.5 hertz.
So it's happening 2 times per 1 second. Frequency is 2 hertz. So 2 times per 1 second. The per second is what makes up the hertz. Hertz is a per second. So it's how many times a second? That's another definition of this. So frequency is how many times a second. I'm looking at the test, and I think I only have 1 or 2 questions. So most of the wave problems on the test actually don't deal with, or a few problems at least, don't deal with light, but it's still the same thing. It's just this equation. It was more general last year. I'm trying to make sure this really goes in. Here's a question. Do y'all know what the speed of sound is? So around here, I think the speed of sound is 343 meters per second. One mile is roughly equal to 1.61 kilometers, or 1,610 meters. Let's say a lightning strikes the ground 1 mile away. So 1,610 meters. How long would it take for you to see it? How long would it take light to travel to your eyes? Yeah, horrible. So you're 1 mile away. Light travels at 3 times 10 to the 8 meters per second. So if the velocity or speed is equal to distance over time, we can solve for time by cross multiplying. So this is velocity over 1. So velocity times time is equal to distance. Just doing some algebra on it, and then divide by velocity. We see time is equal to distance over time, or distance over velocity. So our distance was 1,610 meters. Our velocity for light is 3 times 10 to the 8 meters per second. So for the light to reach your eyes, and that distance is 5.36 carried times 10 to the negative 6 seconds. Alright. What about sound? How long will it take sound to reach you? So this is almost instantaneous. This is quicker than you can blink. And less time it takes you to blink, the light would already hit you. Let's then look at the sound. Well, the sound is going to travel at a velocity of 343 meters per second. Distance is still the same, 1,610 meters. And so velocity or speed is equal to distance over time. It's the same thing. Velocity times time is equal to distance, multiplying both sides by time. And then dividing by velocity, we get that time is equal to distance over velocity. So 1,610 meters. The velocity is 343 meters per second. So 4.6938 seconds. So almost 5 seconds. So when you see lightning, and if you were able to see lightning, so it takes lightning quicker than you blink, so almost instantly. And if you were to count almost 5 seconds, that would tell you it's a mile away. You could use this time to actually figure out how far away something is. If you knew that the speed of the wave is 343 meters per second, you can use this simple formula, velocity is equal to distance over time, to actually figure out distances. I don't have any, I only have one equation, and it's the pair equation that you need to know this equation. I don't think you even know it. I think I tell it to you. Let's see. Where is that pair equation? Most of them I just give you the hertz and the speed. It's a lot of word. The only thing you really need to memorize when doing these problems is this. There's one equation where you need to be able to know this. When it says something like it occurs 20 crests in 60 seconds. So 20 crests in 60 seconds means 0.3 carried hertz. 20 divided by 60. Or if it say it happens 3 times a second, this means 3 hertz. I don't have anything super advanced. As long as you can do algebra with this equation, you're good, and also this equation. Half the test is mostly going to be math like this. Does everyone feel confident using these two equations? It's just, to me, very simple algebra. There's only one problem is tricky. And it's the one that doesn't explicitly say it in hertz. And I think as long as you get that down, it should be good. How many waves is that? So if we were to start here, go around, this is the next identical point. So this is one wave. Continue it right here. That's another wave. Continue it right here. It's another wave. If I were to continue this, that would be 4, but it's halfway in between, so this is 3.5. Does everyone see that? So how many is in this one?
Which one?
This one.
Oh, just a half.
This would be a half wave. Basically, when I say how many waves, it's basically meaning how many wavelengths. It's an equivalent statement. So the test is going to include a lot of problems where you're converting and finding frequency, wavelength, and velocity. Also, relative order. You need to know this. There's a lot of questions like that. Which has more energy, which has more frequency, which has longer wavelengths and such like that. If you start with the radio and memorize it in this order, you can plug in Roy G. Biv. And also your 3 L's are on this side. And the opposite would thus be on the other side. You will have to memorize these two equations. V equals F lambda and E equals HF. In addition to the correct order. Also the parts of the wave. What's a crest, what's a trough, what's an amplitude, what's a wavelength. Does everyone feel confident about taking a test tomorrow over this? I think I've covered everything. I will say that the majority of the test is not multiple guess, which means all this math on solving what is the frequency, you won't be able to guess the answer. You have to actually do it. Things like you see a crest moving towards you at blah speed or blah meters per second. That's the velocity. So this would be velocity. We'll have a test tomorrow over this. I don't think it'll be too bad. Just make sure you memorize the order and write down everything when you get to that.